Hello everyone. My name is Vamsi Kalasapudi from University of North Florida. On behalf of my co-authors Bharadwaj Mantha, Hassan Odeh, and Alekhya Seelam, I'm pleased to present our work titled Text to AR for Home Remodeling, an end-to-end pipeline from natural language to AR compatible 3D assets. The purpose of this research is to explore whether an ordinary homeowner description can be transformed into a three-dimensional asset that can then be viewed in augmented reality. Our work focuses on early stage remodeling communication. The goal is not to produce fabrication ready models. Instead, we want to help homeowners and remodeling professionals establish a shared understanding of proposed design before the detailed design and construction decisions are made. Home remodeling ideas are often communicated through conversations, rough sketches, photographs, or inspiration images found online. These methods are accessible to homeowners, but they can also be ambiguous. A homeowner may describe a modern red sofa, a particular cabinet arrangement, or a customized furniture shape, while the remodeling professionals may interpret that description differently. So, this communication gap that I described earlier can lead to design changes, delays, rework, and additional cost. Existing consumer AR applications have demonstrated the value of placing furniture. They are very technically strong and design objects inside a real room, visually strong as well. However, most of these applications depend on proprietary catalogs containing predefined three-dimensional models. This means the end user can normally select only from the objects that have already been modeled, which is kind of limiting their ideas and their vision. It is much more difficult to describe a customized idea and dynamically generate an AR compatible object, correct? Hence, the opportunity is to convert everyday homeowner language into a visual artifact that both the homeowner and professional can inspect, discuss, and refine. This is where we saw this particular opportunity. Now, in order for us to understand this, we did a literature review and understood that the previous research had made substantial progress in individual areas of this problem. For example, text to image methods produce strong 2D visuals but not deployable AR objects. Multi-view generation methods can create different views of a particular object. Text to three-dimensional and image to three-dimensional methods can reconstruct geometry. However, these capabilities are frequently investigated as separate stages, never put together and investigated specifically in the lines of homeowner to a contractor communication. Many generated three-dimensional assets still require technical post-processing, mesh correction, format correction, manual preparation, and all of that before they can be viewed in an AR environment. Hence, our primary contribution and the research question is, can free-form homeowner intent be converted into an AR-compatible three-dimensional asset through an executable and inspectable end-to-end pipeline? Remember, the most important clarity that we want to give is it does not propose a new foundation model. The contribution is the integration of existing components into a reproducible workflow in which the immediate outputs can be reviewed and improved before the final AR deployment. Now, in order to create this end-to-end pipeline, the proposed workflow contains four major phases. The first phase is text to two-dimensional synthesis, where a natural language description is used to generate candidate object images. The second phase is image enhancement and multi-view generation. The selected image is cleaned, upscaled, isolated from its background, and converted into multiple viewpoints. The third phase is 2D to 3D reconstruction. The synthesized views are used to generate a textured three-dimensional mesh. And the last one, the fourth phase, is AR integration. The reconstructed mesh is converted into an AR compatible format and placed inside a real environment. Now, one of the most important features of the design is that every phase creates an inspectable intermediate output. Instead of treating the workflow as a single black box, the user can review the candidate image, the multi-view set, and the reconstructed mesh before moving forward. This makes it possible to identify problems earlier and reduce the risk of carrying an incorrect interpretation through the entire pipeline. Now, let's quickly discuss individual phases. Specifically, in phase one, currently we rely on stable diffusion that is used to translate a natural language prompt, such as a modern red two-seater sofa, into several candidate images. Now, once we generate several candidate images using stable diffusion by varying the random seed and generation settings, the objective is not to automatically accept the first image. Instead, we provide the user the image that most closely matches his intended vision or design, and eventually let him modify the description and generate another set. So this human in the loop step is very important so that several of the ambiguity that results towards the end product is being, fine-tuned at an earlier stage. Now in phase two, the selected image is prepared for multi-view generation. REM-BG is used to remove the background and create cleaner object boundaries. And real ESR-GAN provides 4 times upscaling to improve spatial details. 0, 1 to 3 plus plus generates 6 consistent viewpoints for sparse reconstruction. These synthetic views approximate photograph taken from different angles and provide the visual information required by the reconstruction stage. Remember, the quality and the consistency of these views are critical because errors introduced here can become geometric artifacts in the final mesh. And that is why it is important for us to include the human in the loop aspect. Now, quickly for phase 3 and 4, phase 3 converts the 6 synthesized views into a textured mesh using instant mesh. The reconstructed mesh is reviewed for geometric completeness and surface stability. When significant artifacts are identified, the workflow can return to previous phase, regenerate the multi-view images using adjusted settings, and repeat the reconstruction. Now the validated model is exported using OBJ and MTL files so that both the geometry and the material information are retained. One current limitation is that reconstruction occurs in a normalized coordinate space. Therefore, the generated model does not automatically preserve the true physical dimension of the object. As you can see in the picture, the placement of that particular sofa. A scaling parameter must be applied after reconstruction. So hence, in the phase 4, the OBJ and MTL assets are converted into USDC format using Aspos 3D. The model is then imported into Apple Reality Composer, where it can be oriented, scaled, and spatially anchored in view in a real indoor environment, which is clearly what the picture shows. Now, this phase demonstrates the practical path from a reconstructed mesh to an asset that can be displayed using consumer-grade mobile AR. Now, in order for us to conduct a case study design, we developed a sofa reconstruction under varied inputs. Now, why sofas, you may ask? It is very common in interior design and challenging for reconstruction due to its curvatures, occlusions, and complex silhouettes. The study included 12 distinct sofa models with variations in shape, size, style, and visual complexity. And our team evaluated front view, side view, and synthetic input images. Each image was tested at various resolutions, for example, 26, 512, and 1024 pixels, respectively. And our team also created high quality and low quality conditions, where the low quality images include controlled blur and noise to represent common problems such as slight defocus, sensor noise, and variable indoor image captures. The quantitative evaluation concentrated primarily on phases 2 and 3 because the consistency of the multi-view images and the quality of the reconstructed geometry largely determine whether the final AR asset will be usable or not. Now, for this particular case study, let me present the evaluation metrics. Now, primarily, we evaluated two different dimensions of performance: perpetual plausibility and dimensional plausibility. Perpetual plausibility evaluated using the Structure Similarity Index, or SSIM. We compared render views of each reconstructed mesh with the original input and with the background removed version of the input. A higher SSM indicates greater visual similarity. Higher is better. However, visual similarity alone is not sufficient for remodeling applications. An object may look recognizable while still having inaccurate proportions. Therefore, we also evaluated width, depth, and height using normalized absolute error, NAE, and normalized roots mean square error, and NRMSE. For both of them, lower is better. So NAE measures the relative error for an individual dimension, where NRMSE provides an aggregate scale-dependent measure across the evaluated samples. For both dimensional metrics, lower value indicates better agreement as described. So hence, all these three measures help distinguish whether the asset is visually useful for communication and whether its approximate geometry is plausible in the AR placement. So quickly, the key results. The average SSIM between the rendered meshes and the original input images was 0.556. When the comparison was made against the background removed images, the average increased slightly to 0.564. This suggests that background elements can reduce the similarity score and that isolating the foreground objects provide a clearer evaluation of reconstruction quality. For dimensional accuracy, the NRMSE was 38.98% for the width, 39.40% for the depth, and 19.16% for the height. Depth was therefore the most difficult dimension to construct. This is understandable because portions of the rare geometry are not visible in the original input and must be inferred from the generated viewpoints. Front views were generally more stable than the side views, while higher resolution inputs tended to improve visual similarity and modestly reduce dimensional error. However, the improvement became smaller at higher resolutions. The main result is that the pipeline can produce recognizable and visually coherent assets for early stage communication. At its current level of accuracy, it should not be used for fabrication or even detailed construction or for precise measurements. Now, the bottom line. This study demonstrates that an executable end-to-end workflow can translate free-form homeowner intent into an AR-ready three-dimensional preview. The central contribution is the integration of text-to-image generation, image enhancement, multi-view synthesis, three-dimensional reconstruction, and AR deployment into one reproducible sequence. The workflow reduces dependence on fixed three-dimensional catalogs and provides inspectable intermediate outputs that support iterative refinement. At the same time, the results clearly identify the current limitations. The generative models are appropriate for design ideation, intent alignment, and early communication, but not for fabrication. Especially the depth recovery and real-world scale remain the main tactical challenges. The comparison shown on this slide is a simplified illustration of the intended use, beginning with an existing room and providing an AR preview of how a proposed object could appear within the space. Now, our team will focus on certain future research aspects, especially environmental aware capture using mobile cameras or LiDAR, scale and clearance checking, room scale multi object generation, user defined measurements, user centered evaluation, and comparisons with direct text to three dimensional approaches. So specifically, we also want to benchmark direct text to 3D methods under the same AR deployment constraints. That is one of the first steps that we are actually taking for this particular research as a future direction. I would love to thank you for your attention. We hope this work provides a practical baseline for future scale-aware and environment-aware AR remodeling systems.